Okay, hey everyone. Today I'm starting a new series called C++ Fully Explained, where I will go into more details than other tutorials on exactly what happens when you write and run a C++ program. So let's start with a hello world, since this is the first video. Before we do a full hello world, let's try something even simpler. Let's just try to return a 0. What happens when you write a main function that returns 0? Well, as we can see here, there's a bunch of push move happening before we actually set something to 0, and then we have a pop and return. The reason why we have those push and move is that we need to do a bunch of stack manipulation on the stack frame to abstract a function call in assembly language. I want to be brief here because there's a lot of details we need to cover in order to fully explain what these registers and assembly is doing. And a lot of you probably have already done the hard work in college, so I'm not going to go into too much detail. If you're interested, you can go into the Wikipedia link. Otherwise, you can think of it as some sort of abstraction around calling a function inside assembly. We also have a return 0. The reason why we set the return value to 0 is not because we don't have any better values to return, but returning 0 actually means there isn't an error. There's a bunch of reserved numbers for returning different type of error in POSIX systems. And returning 0 actually means the program executed successfully. So if returning 0 actually means something here. So let's actually write a CPP file that is what we just described here and compile it. What's interesting is you now see that the file we compiled is 16 kilobytes instead of just a few bytes of assembly that we compiled. Well, that's because the compiled binary file contains much more than what we saw in the assembly. The text section in the diagram is what actually contains the binary. There's a bunch of ELF files header, program file header, and data associated with this binary that will be compiled together. And those blows up the file size. If you're interested, there's a video by Gobbo in CPPCon that is really nice, which covers way more than what I'm doing here, but please check it out. Another thing that you will notice when you have two different compilers compiling the same code of just returning 0 is that in GCC you will see setting the register EAX to 0, but in CLAN you'll actually see XOR EAX EAX. So the difference is here versus here. Well, that's also not something trivial. That's actually because when you have these different assemblies, they have different kind of performance and different kind of binary size implications, although they're doing the same thing. For example, when we have a move command of moving 0 to EAX, it takes 5 bytes to actually express this. That is because EAX takes a Int32 input, and in order to express 0, you need 4 bytes of 0. Whereas if you just want to XOR a register, you just say XOR register something that represents that register, and that only takes 2 bytes. So this is a non-trivial change if you have a big program running with a lot of different changes of values on a register that you need to set to. You can do more reading from the links I provided here. For now, I will just gloss over them. Now let's actually write a hello world. And what you can see here is that on top of the main function, now we have something cxx global var int that is outside of the main function. This is what would actually happen when you have to initialize some global variable before the main function. What's interesting here is that you can see we're calling into some function inside standard library IO-base init that seems to be doing some initialization for the input-output stream. So let's actually take a look at the code and see what's happening here. So what's happening in the standard library in order to initialize standard output is that we have some code that's initializing the stream, and inside this constructor to initialize the stream, we're setting a bunch of pointers that represents standard output from some standard out buffer that takes something, and then eventually we can see the implementation shows the constructor for the std out buff takes a file descriptor, and then we use that standard output buffer to actually put a character onto the terminal. So bottom line is that standard output in a Linux program is going to be represented as a file descriptor, and you can use this file descriptor provided by the system, manipulate it as you would do with any other file descriptor to write content into your terminal. Also, what's interesting in the previously compiled binary is that we only see a reference to a function in standard library, but not the implementation. There aren't any assemblies that's actually doing the initialization for standard output. What's interesting here is that due to the fact that there will be thousands of processes running in a system with the same implementation for IOStream and string and map and vector, that you don't actually want them to contain a separate copy. So what would actually happen now is you would have a bunch of memory mapped to shared libraries, and then when you run a program, the system, the operating system, will try to make sure that the memory mapped region for shared libraries contains your library code that you're referencing, and then when you run the program, it will try to map the function calls you previously referenced to the code in shared memory. What's also interesting is the code that has to live inside shared memory space has to be compiled with something called FPIC, or position independent code, so that other files can actually reference the function inside the shared libraries. So all in all, this is what would actually happen when you compile and run Hello World in one screen. First, you need to compile it with the most efficient code possible, like what we looked in with like EAX, XOR the register itself. And then you also need to leave a bunch of references for functions in shared libraries. So later on, the operating system knows to call the implementation in shared libraries for the code you referenced. When you actually run the program, what happens first is the binary, the operating system is going to load your binary, read through a bunch of headers and see where the instructions are for the text section, and then actually runs code. After that, it will try to map whatever assembly you have in the text section to the shared library space if it's necessary. Then we run the global constructor. In our example, is actually initializing the standard output. And then we actually execute the x86 to write hello world to the terminal and returns a status code indicating that the program has successfully finished executing. Okay, I hope that was a good overview for what Hello World actually does. Please leave comments behind so I can improve, and I'll see you guys next time.